Log on, tune in, find out. Another good idea from Cambridge.
For this morning is Caroline Lasser from the TU München, and our title is Computing Expectation Values for Molecular Quantum Dynamics.
Thank you. So, thank you for the invitation. For me, it's quite exciting to give a talk here. I have the photograph of Dirac in the front asking a question, which puts some pressure on me. But the true title of the talk, which is maybe a bit more technical, is how to use uniform semi-classical approximation for the simulation of molecular quantum dynamics. And one emphasis is also on the word uniform, because I won't exploit any information about the initial data for the dynamics, but the fact that they are L2 functions of norm 1, as they should be for proper quantum system. So most of the results is already published. It is joint work with Susanna Röblitz, and there are some new preliminary results I will also show. So quantum molecular dynamics is governed by a time-dependent linear equation, linear partial differential equation. It's the Schrödinger equation, and so it's a linear PDE. It's rather challenging because there's kind of two things. There's the high dimension of the configuration space your solution psi is living on, and the equation as it is written here is the evolution equation for the nuclear wave function, and therefore in front of the Laplace operator you have a small parameter epsilon, which is something like 1 over the average nuclear mass. So it is really a small parameter, something between 1 over 100 or 1 over 1000, and this means that you have high oscillations on the spatial scale. And by rescaling time in an appropriate way, such that nuclear motion really comes to kind of interesting motion, you also get oscillations on the time scale. So what I also have to explain is the origin of the potential. The potential comprises more or less an approximation of electronic motion, and electronic motion is incorporated in an averaged way. The potential V of Q is for fixed nuclear position, the eigenvalue of the electronic eigenvalue problem, which is a huge issue by itself, and I just assume it to be given. I have a potential energy surface for each nuclear position. There's an electronic eigenvalue, and this electronic eigenvalue steers the nuclear dynamics. So this is what you obtain after the time-dependent Born-Oppenheimer approximation when you want to describe nuclear quantum motion. So as already mentioned in the beginning, for the initial data, there is virtually no assumption but that it is a square integrable function of L2 norm 1. L2 norm 1 meaning that the quantum state or the quantum system has to be somewhere, probability 1. And however, to get an idea of what in practice actually enters into the game, maybe I first show you a cartoon. So what you see here depicted are two nuclear coordinates, And independent of those two nuclear coordinates, you see two electronic eigenvalue surfaces, a lower one and an upper one. And of course, for this is just a reduced model with two eigenvalue surfaces, there will be plenty of them above. And what the talk will be about is about the dynamics on an excited surface. It might be the first one, as in this cartoon. It also might be higher lying electronic surfaces, because the idea of molecular quantum motion is that initially the nuclear wave packet is somehow in a ground state, in a nuclear ground state, in something like equilibrium. Then there is a photoexcitation, there is a laser pulse which falls onto the molecule. There is this Frank Condon excitation upstairs to a higher electronic level. The nuclear wave packet more or less keeps its shape, more or less localization in position and momentum space more or less remain the same. And then the guy sits on top of a hill, for example, and starts to run. And the motion on top of such an excited surface is the topic of this talk. So, just to come back and to give some formulas that you have an idea, the phi naught would be this ground state downstairs, and after excitation it might become a little shift in position, and it might also become a little shift in momentum space. So you might think of a coherent state, a Gaussian wave packet, but you also might think of something, depending upon the laser you are using, you will end up with more complicated structures. But the main idea is that there is somehow some localization in position and momentum for the states you are starting initially. Okay. So the wave function itself, as I already mentioned in the beginning, is highly oscillatory, and there's this very nice drawing of Schrödinger's article on the macrocosm passage in 26, and at that stage he was not yet sure what to do with his wave function, and he depicted here the real part of a superposition of excited states of the harmonic oscillator. And it took until June for Max Born to come up with the interpretation that it is not the real or imaginary part or whatever, but the modulus squared, which gives you the probability density for the quantum system. So, having said this, kind of the next natural step from this quadratic quantity, the probability density, is to move on to expectation values. Even in a laboratory, the experimentator lives on a macro scale and assigns macroscopic quantities like, kinetic energy, potential energy, total energy, whatever you like, position, momentum. We tend to think in classical terms. And translating this to the quantum system, you end up with expectation values. You quantize your classical observable, something like potential energy or kinetic energy, in an appropriate way. You turn it to an operator which acts on square integrable functions with some additional regularity, of course, or decay, in order to make it a well-defined unbounded operator. And then you take the L2 inner product, and if the state is normalized to L2 norm 1, you have here quantities which somehow can be matched with experiment after some, the usual detours when you match with experiment. For the examples of operators I've written down here, the quantization procedure is unambiguous. Q or mi of Q just turns into a multiplication operator, action in p in momentum just turns into differentiation or multiplication in Fourier space. And also here, if you add position and momentum, there is no ambiguity. However, I mean, when you have a multiplicative version of q and p, you have to decide upon the order, whether you first differentiate or multiply or vice versa. And the convention I will use here for the talk will be the while quantization, which takes q and p in a symmetrized way. So when you do so, maybe I just quickly go back to make sure everybody caught the notation. I use a shorthand for the expectation value. So when it is expectation with respect to a state psi, and the observable is the operator associated to the classical function a, I just write a in Langle-Brangle and the psi downstairs. So these are now the quantities of interest I want to compute. And kind of, I mean, the typical way of doing that is you first compute the wave function, and then on top of that you compute the expectation value. This is doable, of course, but I mean, this is a very hard exercise. As I explained, the wave function is a real beast. I mean, it's oscillating in spatial and temporal scales, and it's high dimensions. So this is really challenging. So the point is now just to have another look at those expectation values and maybe enter the game somehow via backdoor. So when we look at an expectation value, and when you come up with the idea of writing an expectation value as a phase space integral over the function which defines the operator, it's a 1.5 line computation, manipulating and using Fourier transforms to see that you have to do with the wave functions the following thing. You have to do an autocorrelation, and then in the shift you have to do an inverse Fourier transform. And then you can represent an expectation value as a phase space average with a proper weight which comes from the wave function. However, the weight is real valued and not always positive. However, there's Garding's inequality, which tells you that for all positive observables, the expectation values are more or less positive, which means for the Wigner function that the volume in phase space on top of which the function is actually negative is rather small. And as a kind of just quick visualization, if you Wigner transform this Gaussian wave packet I had before on the slide, you actually get a positive Wigner function, a Gaussian in phase space. And for more complicated functions, for example, a superposition of two Gaussian wave packets, you obtain a Wigner function which is a superposition of two Gaussians in phase space, and in the middle of the two centers there is an oscillatory term, however with phase space value something like epsilon. Okay, so having discussed this, we go to one of the simplest possible quantum systems, namely the harmonic oscillator. And when you do and for the harmonic oscillator, it's again a very quick computation. When you study the time evolution of the expectation value at time t, you realize that it is identically the same as if you look at the expectation value with respect to the initial datum, and you evolve the observable according to the Hamiltonian flow to the classical harmonic oscillator. So translated to the Wigner function, this is has already been seen in the picture before. So you sample maybe the Wigner function, and then each sample point just evolves around the classical trajectory and ellipse of the harmonic oscillator in phase space. So here, I mean, you somehow see it's a ground state. It's a mobile phone. Or maybe.
Not use.
So I mean, here on that plot you somehow see trivial motion because it's a stationary state, and in the end when you look at the position or momentum density, the guy is circling in phase space, but it doesn't change its contour in that specific case, so you do not really see nothing, but you have stirred the guy with that identity. If we now move on to something less specific than the harmonic oscillator, then we go to the late 60s in this in the formulation I'm presenting here. You are looking at the same type of, now it's not an exact identity but an approximation. The expectation value for the state at time t is approximated by the expectation value for the state at time 0, and the observable is evolved along the classical flow. When you do this, you commit an error, and the error is quadratically in the semi-classical parameter. It depends upon derivatives of the observable. It depends upon the time t, as long as you go for your approximation. Implicitly, I mean derivative bounds of the observable along the Hamiltonian flow, and it is only third order derivatives and higher of the potential which actually enter into the error, which again kind of confirm what we had before. For quadratic potential there are no third order derivatives, so we have an exact approximation. Okay, so this is kind of the first good news. It's not just somehow an approximation, but it's extremely controlled. You have this epsilon square, and you have a rather explicit form of the error constant. But you can go further, work a little bit more, because at the level before, when you just say, okay, there are some derivatives bound along the flow and there are third order derivatives of the potential which enter, if you work harder on the classical dynamics, you can actually move out the time dependence out of the constant and arrive at a somehow reduced approximation order with respect to epsilon, but you get an upper bound for the time interval which is like the logarithm of 1 over epsilon, or the modulus of the logarithm of epsilon. So in the community calls this the Ehrenfest time, because there is 1927 paper of Ehrenfest where he somehow observed that semi-classical approximations can go up to rather long time scales, logarithmically long time scales. I mean, this is just, I mean, there is work in this estimate, but at some point it's also somehow, it's no real improvement in terms of the approximation, because, for example, here in the constant enters instability estimate on the classical underlying classical trajectories, and if you have unstable dynamics, you end up with a bad constant in front of that. So I mean, this is more precision or more control, but there is no real gain here. Okay, but nevertheless, what has been written on the slides before suggests an extremely simple algorithm. So when you just go for the expectation values and nothing else for the of the wave function, you sample the initial data's Wigner function in phase space. You take those sample points and evolve them according to the classical flow. And in the end, whenever you decide to stop, you have a bunch of sample points in phase space, and then you take the phase space average according to whatever observable you want to compute. So this is kind of, in principle, easy. It's conceptually simple. So the idea for that came from Christian Lubich's work on the Hagedorn wave packets, the paper of last year with Erwan Fau and Vasile Gradinaro. They built an integrator which really approximates the wave function itself. And one of their examples, of their numerical examples, is a 2D potential with a torsional potential. And they show kind of there's energy conservation, and then there's the motion of potential and kinetic energy. And they kind of also show, so I just stole that from their publication, kind of energy conservation of their schemes. And you see, I mean, as I already mentioned in the beginning, computing the wave function itself is extremely challenging. And there's, I mean, there must be some defects, and there's a energy drift in the approximation. For large epsilons, it's rather large, and it becomes smaller for small epsilon, but still it's several orders of magnitude. And when I saw that plot, or I read that paper carefully, and in the end I always saw those expectation values. And then I thought, okay, why not just try to do it directly in the way I just sketched before? And then this, really it's not too much lines of code you need. You qualitatively reproduce the dynamics of the expectation values, and you get something like that for energy conservation, which is extremely nice. So you are motivated to investigate further how this algorithm of directly approaching the expectation value really works. So one observation, kind of for the straight lines for the energy we had here, I mean, you just see the error of the initial sampling, and then as time evolves, energy stays straight. This is kind of a property of the approximation. When you look at the energy expectation from the quantum point of view, it's a conserved quantity. But if you look at it from the Hamiltonian ODE point of view, it's a conserved quantity as well. Same holds for mass conservation, or you keep the unit norm by just evolving the constant function 1. Another issue, which is also rather pleasing, I mean, as you already saw, when you do the initial sampling of the wave function, there's a sampling error in the beginning. And when you think about the dynamics, going on this long time scale, which is 1 of order epsilon, you might fear that your error actually blows up over time, depending on epsilon. However, I mean, you revisit the proof, you say, okay, initially I don't deal with the true initial expectation value due to my sampling. I just work with the expectation for a perturbed observable. And what I actually get in my numerical error plots is the expectation value, I mean the difference of the true guy I want to have, the expectation at time t. However, what I actually compute is I propagate the perturbed observable along the classical flow and do the expectation with respect to the initial state. And when you do the error analysis, you see that there enters additively a new term into the error, And this new term is extremely harmless because it's nothing but the time average of the distance your perturbation has from the true guy averaged along the classical flow. And this is just, I mean, of course now you can start and build up a counter example where such a time average is harmful, but in principle this is rather encouraging. Especially since there is no 1 over epsilon or whatever which is amplifying the initial sampling error. Okay, so I mean, with the slides I've shown before, you might ask, why does anybody in the world compute the wave function itself? In the end you just want to see the expectation values. Why just don't do it something like that or something more elaborate? Why are people actually going for the wave function? So one other practical reason for going for the wave function is the following. You can compute spectral information from dynamical information. I mean, I put practitioners because here in that formula, if you actually identify it with spectral information, there is an abundance of modeling assumptions and whatever and they typically use screened Fourier transforms and whatever. But in essence, what is done is one computes the L2 inner product of the time evolved state with the initial state and takes a Fourier transform, and then you get those peaks, more or less, which actually reproduce spectra. Absorption spectra, emission spectra, etc. And if you put something else than the initial data here, but some target space, you are moving toward Raman spectra. So there's this is just kind of seen as a cartoon. It's not just expectation values, but it is overlap integrals, which are of interest, and Fourier transform of them, which means that you have to be very careful about the phase. And that's kind of somehow the real truth why it is really desirable to go for the wave function. And what is now here shown on the slide is the attempt to mimic the program before, which has been carried out for the expectation values directly for such overlap integrals. We do kind of the same ansatz, and what you get on this paper and pencil is the following. You can your expectation value it's not no more, I mean it's now the overlap integral. You have an oscillation you have to compute depending on the Hamiltonian, and you have to evolve everything according to the Hamiltonian flow, and you have to put an additional factor 1/2. This is a formal calculation, and if you now start to worry about the error estimate, you realize that this oscillatory term here in front of your, let's say, propagation, classical propagation, is of course rather unpleasant in terms of error estimation. And in order to control it, you need to put a condition that your initial data are away from zero energy of the Hamiltonian. And I have some encouraging numerical results, but I have no systematic screening about how important that condition actually is. It might be that this condition rules out any practical applicability of that. But in principle, if you just work on paper, you might do the same game also for overlap integrals. Okay, how do you put this algorithm actually to life? There's kind of 3 building blocks: the sampling of the initial Wigner function, the classical transport, and in the end this phase space averaging, which actually gives you the expectation values, the numbers you want. The first and the last step are somehow closely intertwined, because I mean, the way you do your sampling in the beginning, then you have evolved sample points. The sampling in the beginning also suggests how the averaging in the end has to be done. And what you see here, what we have done, we have taken a superposition of two Gaussian wave packets. Maybe I draw the cartoon. So the Wigner function, I mean, this has been done in 2D, which means phase space is 4D. I won't attempt to draw 4D, but kind of the 2D sketch of is that you have two Gaussian profiles, and you have in between kind of a highly oscillatory guy in the middle. And what we have done is kind of conventional sampling of the modulus of the Wigner function, and then in the end, in the final summation, we have just assigned a plus or minus. Okay, epsilon is rather moderate, just 1/10. And you see, so on the left-hand side, you see a conventional Monte Carlo sampling. So you have a Gaussian here, a Gaussian here, you have a Gaussian profile with oscillations. So what you do is you throw three normal distributions and you add everything together. And you really see the central limit theorem. I mean, when you now do different position, momentum, kinetic, potential energy, total energy, when you monitor how well your initial expectation values are approximated with respect to the number of particles, you see as it should be the 1/√n, which comes from the central limit theorem. And so, I mean, this is Monte Carlo, stochastic, so it means you have to do several runs and take the average of that. And you see, I mean, we are now heading for numerics confirming an epsilon square approximation. Put epsilon to be 10⁻�3, so you want to see 10⁻�6 in the end. And here with 1 million particles, you arrive at 10⁻⁵. And this was the point where we decided, okay, we also look at quasi-Monte Carlo sets of low discrepancy, more or less the same principle, kind of the deterministic sister. And if you take good low discrepancy sets, you can obtain an error estimate. Maybe I write it down. So Monte Carlo goes like 1/√n, and quasi-Monte Carlo goes like log n 2D for phase space over n. And so I have not talked yet about the constants, which is not important at the point, but you see the logarithmic term in 4D did not really show up. We more or less observe the 1/n. So nothing surprising. So standard approaches give you the accuracy for the initial sampling you want. What you should do is, for the classical transport, you should use something symplectic. Within a symplectic Runge-Kutta, you get this wonderful straight lines for energy conservation. When you just plug in ODE 4 or 5, you have a tremendous energy drift, which is by no means surprising. I mean, your summation is over, let's say, 1 million phase space points in the end, and if you sum all those, if you sum with a distorted phase space volume element, you're off like that. So the ODE should be integrated symplectically, and then when we go back to the torsional guy, we take one Gaussian as initial datum, and we now vary the semi-classical parameter from 1/10 to 10⁻�3. We look at the different expectation values. We really see, as predicted, the epsilon square. So everything is fine. It is less fine if you, I mean, I talked initially about the propagation of the initial sampling error. and I somehow said, okay, but the initial sampling is really an issue, because here is, so there is another highly oscillatory problem I somehow have put under the carpet so far. The computation of the Wigner function of a wave function is a rather highly oscillatory integration problem in high dimensions. And if your initial data, for example, comes from a grid-based computation of something else, and you go with a, let's say, a stochastic integrator or whatever, you suddenly also have to interpolate your grid-based initial data in order to get your quadrature routine running. And then you end up, for example, we have done something like that. We have really computed the laser excitation of a circular Gaussian, and what you see is what I described in words before. You see a slightly distorted circular shape, and then when you compute the Wigner function, you have this problem of interpolation and quadrature on that noisy data, and then your initial sampling does not really get the accuracy the asymptotic approximation would have. So you see the epsilon is 1/100, so you expect something like 10 to the minus 4, and we were not really able to push our initial sampling to such an accuracy. So there is still room. I mean, how do you really compute an oscillatory Fourier integral in high dimensions? I don't know. So this is kind of, I mean, as long as you can work analytically, or more or less analytically, the initial sampling is no issue. But as soon as you really have to do an integration, I mean, it's not a phase space integration, it's a configuration space integration, but still, it's, this is a real challenge. And the CPUs are just fantastic. So for the torsional potential with the superposition of the Gaussian, if you, so I mean, there are those 3 zones, and you throw 10 to the 3 particles into each zone, then it's a matter of seconds to produce the expectation, and when you improve up to almost 1 million, it's a matter of half an hour. And I mean, as the algorithm suggests, the CPU scales linearly in the initial sampling. And to conclude, there is a 6-dimensional example. Phase space is 12D. So here on the left-hand side you see a projection into 2 momentum coordinates of those 6 with the ball points or quasi-Monte Carlo. Random means normally distributed, Halton again. And you see, I mean, as you move to higher dimensions, there are some issues about high-dimensional sampling, because I mean, you see that there are those strings and alignments, which is something you do not want to have. But nevertheless, this, to produce such a plot of kinetic and potential energy, has been a matter of exactly 3 seconds on that laptop computer. Because it's, I mean, it's clear, you generate your sampling points, and then you go with an ODE, and you see, I mean, this is now for 6 cycles, but I mean, you can go up for something like 10, 15 cycles until the thing starts to deteriorate. But of course, if you take different dynamics, you can also put the collapse a bit earlier. Okay, so thank you very much.
So, do we have a question inside? There is one question by you to the audience, which is how you compute this high-dimensional highly oscillatory integral.
Yes.
So we have 20 minutes to solve the exercise. No particular question? So,
Well, one question. Do you have to evaluate this oscillatory integral for every particle? What kind of evaluation do you have in mind? Because it's on a high-dimensional space as far as it's.
Yes. I mean, maybe I go back to the sketch of the algorithm here. I mean, if you want to sample something, you have to know it somewhere. Oh.
So do you perform sampling on a regular grid in 6 dimensions?
No. I mean, what I propose is really, as I wrote here, Monte Carlo or quasi Monte Carlo or what. I mean, you cannot set up a grid anymore. But nevertheless, on those random points, yeah. I mean, here, also here, for those Gaussian guys, you just do a simple Monte Carlo by drawing from a normal distribution or 3 normal distributions. And with something more complicated, you set up a Markov chain with stationary distribution, the mod of the. But I mean, you don't need to compute the guy everywhere. But I mean, if you think about a Markov chain and you want to evolve the chain, you have to compute it in order to decide where to move next. And I think also for the Hagedorn wave packet solver, if you want to decompose an arbitrary initial data with respect to the Hagedorn wave packet, you end up with a similar. Not the same, but I mean then there's again you have to compute an overlap with the wave packet in order to get the coefficient, and then there's similar flavor to that type of. So kind of you need, I think every type of semi-classical approximation needs a phase space representation of the initial data. And I think this, I have some time, so maybe I can. I think this is one of the reasons why in the chemical physics literature, the semi-classical approximation does not have a good reputation. And I think one problem is that people are extremely careless with their initial sampling, and they do not really care if they actually represent the initial data they want to work with.
The initial data, the Wigner equation is complex, right? The initial data for Wigner function. So when you select the particles, how can you take the phase complex information?
No. I'm here, I skip back to the definition of the Wigner function. The Wigner function is a real valued function. When you look at this question here, and you just compute the complex conjugate, you see that it is a real valued function. It would be different for the, if you go for Raman spectra. If it really works out to compute overlap integrals, then the initial thing you have to sample would not be the Wigner function, but the Wigner-Moyal function, which, so maybe I'll write it up here. So it would be kind of the same thing, but morally it would be a Fourier transform in the translation. I call it Y. But you would have the psi, you do not have the autocorrelation function, but you have the correlation function. And you Fourier transform in the shift, and this guy is complex valued. And then you have to address questions of complex sampling. But not for the expectation values. And this just also, this just comes when you go for Raman spectra. For absorption spectra, it's still the Wigner function, and the Wigner function is real valued.
But it will happen after 2.
No. The Wigner function is real valued. Point.
Yes. So given that we have almost all the experts in the world on computing highly oscillatory integrals in this room, I wonder whether others will agree with me that actually this is a very nasty integral to compute. Because you are integrating over the entire phase space.
Yeah.
and then it converges too fast in epsilon. So when epsilon decays,
Yeah.
the integral, the asymptotics of the integral are spectral. They are not polynomial. We have very good methods for polynomial asymptotics. Had you had a nice stationary point, no problem. But it goes too fast in epsilon. So the only thing remaining essentially is FFT. But QMC or MC won't work with FFT because you want either totally random configuration of points or points on some sort of clever grid like Sobel grid. So I don't think that there is any good method that has come to my mind. With it, I wonder whether other people have anything more intelligent to say.
Thanks for the motivation. So, is there any follow-up on what Ari said?
Well, I think what he said is correct, yeah.
Okay. Any other question on another or any remark? No? So thank you again, Charlie.
Thank you.